morning, everyone, and thanks for coming. I know we have a mixed crowd in here, so hopefully this is going to be a really good talk for lots of different backgrounds and interest levels. If you don't know me, I'm Cassandra Berincott. I'm a mechanical engineering faculty, and I've been here 10 years, and so right before I arrived, I actually knew this character, so I get to the privilege of introducing Dr. Hart today. Dr. Hart is currently an assistant professor at the Milwaukee School of Engineering in Milwaukee, Wisconsin. He received his BS in engineering mechanics from the University of Wisconsin-Madison in 2010, and then a PhD in aerospace engineering from the University of Illinois in 2016. That number right. So that's actually how we know each other a little bit. He's currently the principal materials engineer for Prepared for Flight, which is a technology company focused on the commercialization for novel additive manufacturing filaments, and that's the topic that he's going to talk about today. So with that, welcome Dr. Hart, and we'll let you take the floor.
Awesome. Thank you, and thank you for coming this morning, 9 a.m. Sorry if you're expecting a different Kevin Hart. Let you down. You know, I'm Dr. Kevin Hart, not that comedian you might know, but I'm just as funny. You'll see. Okay, so we have a topic that hopefully is interesting to people of all backgrounds, mechanical engineering, polymers, whatever. And that's 3D printing. So today I'm going to talk about some work I've done on 3D printing and actually how to just make 3D printed parts a little bit better than they currently are. So let's get right into it. I think many people here have probably seen 3D printing, but for those that maybe have not, I'm working on polymer additive manufacturing, a specific type of 3D printing called fused deposition modeling. Probably the one that you're most familiar with if you've ever seen it. You have some plastic filament that goes into some heated nozzle. It's like a hot glue gun on a gantry. Kind of moves back and forth. You can build up a structure layer by layer. Here we have a little elephant that we're building or showing or demonstrating and building this layer by layer. Here's what it actually looks like in practice. And there's a lot of different filaments and polymers that you can use to do this. So I always like to pass around this little sample here. This is called a benchy. It's a very common like 3D printed item. If you've ever 3D printed something and you want to know sort of the quality of your 3D print, you might print a benchy. We'll talk a little bit more about the benchies in just a second, but there you go. That's a 3D printed object that's made out of ABS, one particular type of plastic. But you know, 3D printed objects, they're not often used in engineering application, and mostly because they have a really weak inner layer strength, right? So if you're printing something layer by layer by layer, you tend to have a very weak inner layer between those layers of the print. And so a lot of people have demonstrated this in a lot of different ways, whether it's tension tests, flexure tests, compressive tests. And so we're just showing that a little bit here, is that no matter how you sort of orient a typical dog bone, it's going to fail like sort of at the interface between like those weld lines of the 3D print. So you can see that with dog bones printed with various raster angles. These are 4-point bend specimens that were tested in flexure, and so you see a lot of failing at the weld lines, and it's pretty evident when you sort of just look at this visually that that inner layer is particularly weak. Okay, you can put some numbers to this by sort of making dog bones of your own. So there's an author that did this in 2016, and I just like his data because he just did a lot of cool stuff, where he made dog bones that were oriented in 3 different orientations. A horizontal, so kind of like, you know, the raster is going this way, sort of the side profile, and then a vertical profile. And in this situation, you'd expect the vertical to tend to be the weakest because that's where the stacking or the layering is occurring. So if you're loading across that layering, you'd expect quite a bit of weakness. And you can just sort of look at, if you're making a dog bone and it's laying on its side, this horizontal orientation, you get a tensile strength. This person tested at about 32 MPa, but if you sort of go in this vertical orientation, there's some dependency on the rastering directions that you choose, but anywhere from 12 to 20 MPa. So significant reductions when you start loading sort of in this direction where the weld lines are sort of perpendicular to the direction of loading, okay? So this is not something that I observed myself for the first time. It's like pretty obvious to understand this idea. And when I thought about this, I thought about, well, what is really the difference between something that might be injection molded that you test versus a 3D printed object that you might examine, all right? So if you've taken a strength of materials class, you've probably done something like, okay, this failure strength is the load divided by the cross-sectional area of the object. So you go to your lab class and you make these dog bones and you pull on them, and when you're doing that and you're investigating this stress to failure, you're taking the max load divided by the cross-sectional area. This is really like investigating the strength of the material itself. So you'll see like necking, if this is a, let's call this ABS again, plastic. Ultimately, you'll see some weighting probably if there's plasticity, and then it's going to fail, all right? But 3D printed objects, especially ones that have this rastering pattern and this layering across the direction of loading, they're not really governed actually by failure of the material. There is a little bit of that going on, but most of the time they actually fail prematurely because of sort of the ridges on the side or internal surface flaws that might occur that cause stress concentrations and stress intensity sort of at the edges where the surface flaws are that sort of just propagate through the material and break it in half a little bit more quickly. And this whole idea of like there's a notch or a crack inside of a material that causes propagation of that crack to get the material to fail, this is kind of getting into the realm of fracture mechanics. And so maybe there are some people who are studying fracture mechanics. I think we have some younger people here that may not have seen ideas of fracture mechanics, but the basic idea is that it changes the idea of how you want to analyze this failure from your traditional load divided by cross-sectional area to fracture mechanics that rely on a metric called the stress intensity factor or critical strain energy release rate, depending on sort of what metric you're using. So you might see this as strong if it's injection molded, and you might see a 3D printed sample as weak when you're testing any tension. But it didn't really make sense to me personally to look at like tension testing because it's really, you're investigating fracture, not tension. So one of the very first questions I really had when I was sort of thinking about 3D printing personally is, can we like evaluate this interlayer strength here to come up with like a better number than just like a tension strength, okay? I want like a fracture strength, like between the layers. Like what is my interfacial strength between those printed layers? That's what I'm after first, okay? So one of the first things I did is I manufactured a fracture specimen. This is called the single edge notch bend specimen, SENB. It's just this rectangular prism that looks like this, and it has a small notch on the underside. You put this thing into 3-point bend, and there's going to be a crack that propagates from this notch tip forward. You can use cameras to sort of look at how far the crack is going, and you can get a metric associated with how much energy it takes to propagate a crack a certain amount, okay? That metric that you might be interested in is called the critical strain energy release rate. It typically has a variable J1C or G1C. Not important, but the idea is that we're going to measure this critical strain energy release rate, J1C here, and the units you can use to sort of understand what this is, joules per meter squared. This is a measurement of energy in joules required to create a crack of a certain size, meter squared. So how much energy does it take to create a crack of a certain size, meter squared? So for a typical injection molded ABS, so like a normal polymer that you might use for injection molding, this J1C value is a material property, a lot like stiffness, you know. You can measure this using a sample that looks like this, and this particular ABS that we're going to talk about is in the range of 4,000 to 6,000 joules per meter squared. So keep that number in mind because I'm going to talk about 3D printed samples in retrospect. Here's a single edge notch bend specimen that we tested. Okay, you can sort of take a look at the crack underneath, and you can sort of see the whitening in front of the crack tip. That's some of the plasticity for those of you that are interested in that sort of stuff. The crazing, the whitening in front of the crack tip, giving you the toughness that you like. All right, so now we take that idea, this is for an injection molded, but I want to do this with a 3D printer and sort of test this interlayer strength between the layers of the 3D printed sample. All right, so we build this rectangular prism, the single edge notch bend specimen. We put in a pre-crack inside of the sample, like between two of the layers, like in the middle of the print. And now we're going to test this guy in 3-point bend and evaluate its critical strain energy release rate. Compare that to like an injection molded sample. All right, so we did this. All right, this is what it looks like. Here's my rectangular prism. Here's the pre-crack on the underside, and the crack is going to propagate from this notch upwards. So you put this into 3-point bend, load it, load it, load it, load it, load it. And what you'll notice is that the crack propagation is like very sudden. It's almost like breaking a pencil, right? You load, 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 and then it just snaps. All right, load this guy, load this guy, load this guy. The energy builds up at the tip, and it just like snaps forward and fails. All right, so we take that energy, it's the area under the curve, divided by the crack opening that we made, more or less. And we come up with a value of about 250 joules per meter squared for a 3D printed sample. So if you compare this value to this value, very easy analysis, this is big, this is small, okay? So what that tells you is that an injection molded ABS sample has a toughness of about 4,000 to 6,000 joules per meter squared, but the inner layer of a 3D printed sample, 250 joules per meter squared, very weak, that interfacial strength, very weak. And this is more or less the big problem or crux of 3D printed samples and why they're not used in 3D, like in engineering application very often, just because this interlayer strength just sucks, okay? So you got to do something here, all right? So then I made the next step. Is there a way to increase this interlaminar toughness, and how do we do this? Okay. Well, I'm not the first person to try some various things, okay? So let's talk about some of the other things that people have tried. One thing that you might want to try is changing the temperature of the nozzle during the 3D printing process. So when you're 3D printing an object, you can control the nozzle temperature. For those of you that haven't 3D printed, a higher temperature might give you more flow of your polymer and create a better bond, right? And so that's what these people showed. They made, these are called compact tension specimens. These are out of PLA. And when they printed using a nozzle temperature of increasing temperature, they found increasing toughness. So larger area under the curve for the same crack opening gives you more toughness for your sample. Okay, so that's one nifty way to do it. But their results didn't get you anywhere near like the injection molded strength that you would want out of like a really good engineering material, right? So that's one way that it can be done. There's some other slicker ways that people have tried to do this. Another kind of interesting technique that was coming out of Texas A&M was people were making filaments that had carbon nanotubes around the very outside of the filament, and then using microwave irradiation to like excite the carbon nanotubes at that like printed layer between the two interfaces so that the polymers would like migrate across that interface and you know, recover that interface. So basically like putting your sample in a microwave and locally heating it at the interface so that it would like weld between the layers. Okay, so they're visualizing that by saying, okay, here's polymer spaghetti of layer number 2, here's polymer spaghetti of layer number 1. Now we're going to put this in a microwave and they all commingle together and heal that interface back together. All right. So for those of you in polymer physics, you've probably seen some ideas of polymer spaghetti that looks like that and how those polymer chains migrate under various stimuli, Brownian motion. I don't know how much you get into like that sort of stuff, but this whole idea of getting these polymer chains to move across an interface or generally move within a polymer was pioneered in the 70s by a French scientist named Pierre de Gennes. He actually won the Nobel Prize for his work. Pretty interesting stuff. His theory is called reptation theory. This idea that polymers live in these tubes, these chains, and you can excite them out of these tubes using energy, temperature, UV, whatever, and get them to migrate and move. And the whole theory here is that, all right, we got 2 layers of our 3D print. Layer number 1 has some polymer chains, layer number 2 has some polymer chains, and we're going to excite those polymer chains and get them to migrate over the interface using this reptation theory. It's the same like base word of like reptile, right? Snakes slither like reptile. These are like snakes, polymer chains like moving inside your material, all right? It's the same general idea. All right, so that's reptation theory, and we'll come back to this a little bit later, right? So, very primitive. One of the first things that we wanted to do is understand, all right, we want to do this reptation. We want to basically take our 3D printed sample, get the polymer chains to move across the interface using temperature. All right, so let's 3D print our sample. Here we are. We know that this is generally like low strength and low toughness, right? It sucks. We never use it in an engineering application. Then we're going to apply some heat to it for some amount of time and transform it into like a injection molded piece just by basically melting it together, right? Very primitive, very crude, but the whole idea here is that science is working in steps, right? We got to figure out like what time and temperatures are required, how long does it take? All the physics that go into this are important to us, okay? So this is step number 1, figuring out what annealing is required, heat and time, right? So we did this. Again, we made our 3D printed samples, these rectangular prisms. We're going to do this fracture testing on them, where we put them in a frame, and the crack is going to propagate upwards. We're going to measure how much energy that takes, etc. But this time, we're going to anneal them. And what I mean by that is I'm going to take these 3D printed samples, and I'm going to put them in a mold that looks like this. This is an aluminum mold. There's some aluminum spacers between, and we can slot in our single edge notch bend samples. They're, you know, maybe 4 inches long. We got one going around inside the audience right now. They're like 4 inches long, maybe like a ½ inch wide. So we can slide a bunch in there, put it in an oven, and then anneal them for certain times and temperatures and see how that affects their interlayer toughness by doing the fracture test. Okay, generally. So we picked a bunch of annealing times and temperatures that were, you know, selected intelligently, and let's see what we get. So here's the rub. This is the data that comes from that simple test. Okay, here we have on the x-axis annealing temperature, the y-axis, this is your interlayer toughness, your critical strain energy release rate. If you anneal the sample at room temperature, which is basically just you 3D printed it and then you tested it, we know that that toughness is very low, about 250 joules per meter squared. This is kilojoules per meter squared, right? So 250 joules per meter squared, very low toughness. If you then anneal this thing at 75 C, let's say, for 2 or 18 hours, that's the 2 different lines that you see here. If you anneal it for 2 hours, 18 hours, you get a little bit of benefit, right? If you anneal at 75 degrees, you can maybe go up to like 500 joules per meter squared. You're kind of getting some sort of interaction between the layers at that point, but not a ton. But if you start to increase your annealing temperature beyond the glass transition temperature of ABS, then you start to see some melting of the layers into each other, more or less. You start to see some increases in the toughness. But if you really blast this thing, go up to 175 C, you'll start to get toughness values here 6,500 joules per meter squared, right? So 6 kilojoules per meter squared, and beyond. So this is your injection molded strength that we talked about before, 4,000 to 6,000 at the inner layer or for a fully dense material. And now if we anneal, we get layer, levels that are equal to or greater than injection molding. So basically just taking the sample, putting it in a mold, heating it up, it flows, it melts, then we test it. Okay. So wonderful, that's great. But you did it in a mold. Like, why did you 3D print this if you have a mold? Makes no sense. All right, why not just like injection mold it? Okay. Like, duh. You just like printed it and then you just melted it. Like, that's stupid. Okay. All right, fine. I give you that. All right. But it allowed us to learn some physics about the situation. This is why we did this. Okay. So when you think about what has to happen if you take some single edge notch bend specimen that looks like this, you put it in your annealing fixture, there's some time scales that are required to basically get this thing to heat up, and then some physics have to happen for those layers to like melt into each other. All right. So step number one is you have to figure out how long it takes to get your sample to heat up. You guys take heat transfer. And this, most of you have taken, how might I determine the time scale that it takes for this thing to heat up? Challenge question, maybe bonus extra credit. How could you figure this out? I believe in you.
I only see a couple that have taken heat transfer anyway. Calling out a couple.
Thermal resistance model. Hear that? You make the little resistors. Thermal resistivity. Okay. So you can determine about how long it takes to get this thing to heat up, a time scale. How long do you think it takes generally to get that thing to heat up? I take that little 4-inch by 1/2-inch rectangle. How long might that take to heat up? Just guess. In an oven to 100 C. 18 hours, right?
Yeah, sure.
No. Okay, come on. How long does it take to cook a pizza? Like Jesus. Yeah, like 5 minutes, right? Okay, not that long, okay? So you can do this calculation yourself, even as undergrads, I believe in you. There's also some physics that have to happen between like the 3D printed roads that you print, right? So you've got these like 3D printed lines that are next to each other and they actually have to like migrate into each other. And there's this whole like body of literature about this. It's called sintering. So there's a lot of polymer processes that rely on sintering as well, but this whole process of like getting those two layers to kind of like meld into each other, it's called wetting. And so there's a whole body of literature associated with that, okay? Then lastly, once those things have like made intimate contact and like wetted with each other, this reptation has to happen, which is, again, back to our French scientist, Pierre de Gennes, talks about the timescales associated with reptation. So, there's math behind each one of these things that you can go through and tell yourself like, all right, what's the rate limiting step? What am I learning about like this annealing process? So you can sort of guesstimate or use math to sort of give you in the ballpark about how long each of these things take, okay? Heating this thing up, we know it doesn't take all that long. Cooking a pizza, 15 minutes, right? This reptation, which is these polymer chains migrating across the interface, turns out that actually occurs really quickly if you're above the glass transition temperature of the polymer. Very, very fast, about 1 second, in comparison. But it's this like intimate wetting actually that really takes a long time, like this wetting. These two roads, they have to sort of like melt and sort of like meld into, it's like raindrops on the car window, right? You got the two raindrops hitting each other and then they like absorb into each other. All right, it's like the same kind of idea here, except you're doing this sort of at, a stationary state, right? So there's math associated with these, but this wetting is sort of the rate limiting step. And you can sort of go through the math and make some models and predict about how long it's going to take for this intimate contact, this wetting to occur. And so we have a characteristic time here, this TS, that's dependent on the viscosity of the material, the radius of the road, and then it's inversely proportional to the surface tension between the two items. All right, so all these things are generally known. If you're 3D printing something, you'll know the viscosity as a function of temperature, you should know the surface tension, and the radius of your road is just whatever the nozzle size of your 3D printer is divided by 2. Okay. Then we're going to say that there's some maximum toughness that we can achieve. This is our injection molded strength. We'll call that J infinity. And then we have just a very simplistic sort of Arrhenius type model to predict, using a characteristic time, what the toughness will be given a certain viscosity and surface tension that are dependent on temperature. Okay? So knowing the temperature, we can sort of have a dimensionless time that tells us about how long it's going to take for us to get to injection molded level strength, depending on our it's a dimensionless analysis to help us determine how long it's going to take for us to get to a fully dense state from a 3D printed state. Okay, so it's just some math here showing how that is done. So the wetting dictates the healing, and we have a little model. Cool, models are nice. All right, but like we said, we cheated. All right, shame, shame. We put these like single edge notch bend specimens in this aluminum mold, and if you're going to 3D print something, why use a mold in the first place? So if you were to actually take that single edge notch bend specimen and try to anneal it outside of a mold, it looks like this. Okay, so we'll pass this one around too. Don't break that one; it's very important. I'm just kidding. You can break it if you want. So if you try to do this annealing outside of the fixture, it looks like that. So you got to do something. You can't just. That's not acceptable, right? You can't use that, right? So can we do something here now to allow annealing to occur, but not get this weird distortion that might come from raising it to a temperature above its last transition temperature? So how could you do that? Okay, that's the next step in the journey. And so we came up with a relatively clever idea. And this idea is to use a filament in the 3D printing process that's actually made of two different polymers. So in this particular example, you might have a red portion of the 3D printing filament that is ABS, what we call a low glass transition polymer, and the white portion of the 3D printing filament that is a high glass transition polymer. In this case, we use polycarbonate. So the glass transition temperatures of these two different polymers vary by about 50 degrees C. And the idea now is that we're going to take this 3D printing filament and print a structure using that filament. And so if you printed a structure using that filament, the mesostructure of that material might look something like this. You got like all this white that is polycarbonate, all this red that's ABS. And the idea here is that we're going to now anneal this thing at a temperature between the glass transition temperatures of the white polycarbonate and the red ABS. So the idea there is that the annealing will be such that the red ABS will flow and do all that wetting and reptation and all that good stuff that we want, that healing of the interface. But the white will just stand strong and be a skeleton, so that it doesn't deform during the annealing process, right? It's like your backbone, your skeleton, that doesn't, deform during the annealing because you're not annealing above its glass transition temperature. Okay, it's the general idea. But this filament doesn't exist. Okay, so we have to figure out a way to make this ourselves. All right. There's not a lot of dies that exist for like a traditional barrel extruder that could make something like that. Okay, so we got to do something else. If we want to visualize this a little further, I like this image. It's like the toothpaste image, I call it. So it looks like I'm squeezing toothpaste out here. But, all right, I'm 3D printing with my filament layer by layer. I'm going to do some annealing, right? The red ABS will flow. The white polycarbonate will not flow. It will just sort of give you a skeletal structure so that it doesn't deform. So how will we make these filaments? Well, let's use 3D printing because that's what we do. All right. So how are we going to make these filaments? All right, here's the process. I'm printing an ABS, what I call preform. It's maybe 1 inch in diameter. And I'm going to print polycarbonate separately. That's going to be the core that goes inside of the blank ABS. Then I'm going to take my arm and push them together. All right, so I shove the polycarbonate into the ABS. And I have maybe like a 1 inch diameter, what we call a preform. And then we were inspired by how they make like these sugar candies. You guys ever see like the candies with like the little butterflies on them that are maybe like this big? Okay. The way that they make those is they start with these massive like 8 inch diameter like sugar things, and they put it in a vertical furnace and they pull on it and they draw it down. And that cross-sectional geometry retains down to like the size of a candy. All right. We're going to do the same thing here. We're going to take ABS, we're going to take polycarbonate and jam them together and then put it in an oven with heat so that we can pull on it and draw it down into filament that has the cross-section that we want. All right, it's just a drawing down, pulling down this filament to make the cross-sections that we want, okay? So this is what it actually looks like, all right? So this is a little preform that I stopped in the middle of the process. You can see that we 3D printed the polycarbonate and the ABS separately, and we jammed them together, and then we put this into our little conical furnace, and we pulled on it in a very controlled way so that we could make a diameter in a filament that had a cross-section that we wanted so that we could feed it into our 3D printer. So I'll pass this around. Here we go. And I'll also pass, here's an example, just I cut a little bit of the filament. I mean, we have like spools and spools of this, but test your eyes, okay? See if you can see like that star shape in the cross section of this guy. Right? So we made this star shape, and now we're going to use that to 3D print a structure. We're going to anneal that thing, and it's going to weld at the interface, but not lose its geometry because it's got that polycarbonate skeleton inside of there. Right? And then the question is, well, what shape do you want your filament to be? Well, the beauty of this 3D printing process that we use to make this filament is that we can make filaments of all different types of cross-section, right? You can make the star shape, which we have here. We've done concentric polycarbonate ABS. We have like we call this a 3-spoke. This is a 3-spoke with flange. This is a 8-spoke, 5-spoke with flange. You get the idea, all right? So we were just kind of playing around, seeing like which filaments might be best for this process. So we had a lot of these different filaments, and I potted them in a puck of epoxy. So if your eyes are good, you can sort of take a look at this little puck and see the filaments with the different cross sections. It's kind of cool. There's like a concentric one in there. There's like a 5-spoke. You can sort of just like take a look. Okay, onward. So what we did is we went back to our fracture sample. Took our 3D printed filament that we drew down in our draw tower, made all this filament. Now we're going to make a single edge notch bend specimen out of that material, and we're going to evaluate that in fracture. So make this guy, do the annealing for a certain time and temperature. Here we picked 135 for 72 hours. And that's going to increase the toughness because we have this material here now. Okay? So now we're going to do our fracture test. Here's the initial crack. The crack is propagating. We see this whitening, which is, called crazing, or just signs of plasticity inside of the material, and the crack is propagating. We're measuring the energy associated with that crack propagation. We know the area. We can determine our fracture toughness using that. And this is a sort of a smattering of a lot of the results that we have. So let's first start with our control, just our blank, typical ABS filament that we've talked about for the first 15 minutes of this talk, right? So if I print a 3D printed sample with just ABS, and I do not anneal it, we know that the toughness is about 250 joules per meter squared. If I anneal it inside of a fixture, I get toughnesses of 7,000 joules per meter squared, like injection molded levels, right? Here are all the results that come from printing those fracture specimens, annealing them, and then testing these guys in fracture, using the various filament geometries of, we made a lot of different types. The best performer was this like star-shaped filament that looks like this, and that gives us 16 times the nominal toughness, and you get about, 4,000-ish joules per meter squared, which is getting to injection molded levels. Basically, we've achieved injection molded levels. All right, so pretty awesome. You just have this filament, feed it into your 3D printer, take that thing to an oven, anneal it, and now you're at injection molded toughness. Pretty sweet, okay? No longer need the mold, by the way. This is all done without that, aluminum fixture. So, pretty cool. All right, this is more results. We'll send out the slides if you're really interested. Okay. So, just to conclude or put a bow on this little section, 3D print the ABS and the polycarbonate separate. Jam them together. Put it in a draw tower, draw it down to filament that you can use in your 3D printer. We looked at a lot of different filament types. The idea then, feed this into your 3D printer, 3D print an object, anneal it, the ABS will flow, heal your interface, the polycarbonate stays so that you don't lose your geometry. Got it? Awesome. All right, we had a lot of stuff that we published and patents, and if you want to read more about it, there you go. All right, some pictures, because pictures are cool of these various materials. So the bench sheet that I passed around, we made a bunch of those like out of various materials. Here we made it out of pure polycarbonate. Here we've made one out of our DualMaterial. This is our polycarbonate core and our ABS shell. And this is one that we made out of ABS alone. We annealed all three of these at 135°C for 3 days. The polycarbonate survives because its glass transition temperature is 150°C, and we annealed this at 135°C. Our DualMaterial filament printed benchy also survives because it has that polycarbonate skeleton inside of it. Okay? But the ABS, when you print it and it doesn't have that polycarbonate skeleton inside of it, it just, you don't want to get on that boat. You know what I'm saying? All right. That guy didn't quite make the trip. All right, cool. So that's great, but there are limitations, of course. The biggest limitation of this is that you can't really make the filament that quickly. So this methodology that we used, where we sort of print this guy, jam them together, put it in an oven, pull it down, blah, 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 blah. You get maybe like half a spool of filament out of that for like a day's work, all right? Not ideal, okay? It takes a long time to like make this filament. You don't get a lot of like production out of it, okay? So it would be nice if you had a method to more quickly make this filament, all right? Another thing is like doing this drawing process, it's not stable. It's a little bit like my personality, all right? Unstable. All right, diameter variations are common, which is bad. If you're a commercial filament provider, you're aiming for filament diameter, if you're using 1.75 millimeter filament for a 3D printer, 1.75 millimeters plus or minus 0.02 millimeters, all right, 20 microns precision. It's not unreasonable, but for us that was hard to do because this drawing process is it's like freehand almost. I mean, we had a machine that was like controlling the take-up, but it's actually hard to control that drawing process like really tightly. Like this process here where we're just kind of like pulling it down, taking it up. It's pretty hard to actually control that to the level that we needed. It was close, but not perfect. Okay, ours might be in the range of 1.65 to 1.8 millimeters, which is suspicious. All right, sus, as they say. All right. So how might we scale this up? Well, if you're going to make 3D printing filament normally, you would use a single screw extruder, something that looks like this. You've got a hopper where you're going to put your pellets of ABS in there. You've got a screw that's being driven by a motor here on the back end, pushing all of that polymer pellets forward, and then you have all these chambers here that are heated to various temperatures. On the back side, you have a die. It's going to give you circular filament, and you can run this thing all day long, make tons and tons and tons of filament. That's how most filament is made. All right? At high rates of production. Then the question is, well, can we make something that looks like this to produce a filament that looks like this? All right? Okay, maybe. Let's try it. What we're going to use is there's a company across the pond in Great Britain that makes a very specific type of extruder. It's a DualMaterial extruder. So these are two barrels next to each other. So if you can imagine this picture, but we have two of them now. You've got one motor that's pushing this barrel, one motor that's pushing this barrel. You can control the temperatures of each of the barrels, and then they come together in this die housing here, and you can flow the polymers inside of this die housing by making a die that sort of controls the flow of the two polymers as they're coming through this barrel and this barrel. And getting a single material out the backside just relies on how you made your die sort of to put inside of this housing. So these two motors are actually helping push the filament down as well. So this is a machine that we used. There's a machine in the Boston area that we found, somebody has it. And so we went there and said, hey, can we use your machine? And he said, who are you? And I said, I'm a scientist, it's okay? He said, okay. So then we did this. We put ABS in this guy, we put polycarbonate in this guy, and we ran this machine, and we created our own custom die for this housing to see if we could get this to go. All right, here's pictures of the machine. These are the two hoppers on the backside. This is the motor that's driving barrel number one. This is the motor that's driving barrel number two. This is kind of a side view of it. So you see the barrel sort of from the side here. This is the control panel for this whole assembly. So you can control the temperatures and the flow rates of all the different barrels and things like that. And then maybe you see the die housing where it's going to come out is like right here. And so here's sort of another view of us actually making filament. So here's the die housing where we have some die that's controlling the flow of both ABS and polycarbonate to make us filament. The filament's white now. We just have both natural polycarbonate and natural ABS, but okay. It's white instead of red, but both materials are in there, I promise. So you see the filament coming out, and it's coming into a water bath. It's making a turn at this pulley system that helps us guide it. And so here we are, making filament. The die design was the work of a graduate student. So there's a master's student at University of Massachusetts at Lowell that, when I sort of talked about this problem with them, they said, all right, let's make a master's thesis out of it. And so some guy designed a die to help with this problem, making this filament of this particular cross-section on a barreled machine. So this is sort of a axisymmetric, more or less, cross-section of the die. We actually 3D printed the die because, of course, we did. The die is metal 3D printed now instead of polymer. So we have sort of a die here, and it allows the ABS to kind of come around and be sort of the shell on the outside. And then there's an opening here on the inner die that has a star shape. And we sort of like did a lot of parameter variation of what that star needed to look like so that our final filament actually had the star that we sort of want. Okay? A little bit difficult to see, but these are some of the undersides of some of the dies. So if you're like looking from what would be like this bottom side, kind of like looking at the bottom of this surface here, this die surface, you can sort of see some of the star patterns on some of these dies, and then the resulting filament that kind of came out of the line when we did this. This is, you know, a little bit of chaos here, not the best, a little bit more refinement, and now Patrick of SpongeBob fame is just what happened. Okay? So, pretty good. All right. So we're starting a business. Trying to make and sell the filaments, and so far it's okay. We're now making a filament that looks a bit like this, not fully refined yet. We're still working on it a bit, but we're able to make filament with this particular polycarbonate in the center, ABS on the outside. Shape, you can feed this into your 3D printer. You can make anything that you want. Anneal it for a certain time and temperature, and then you have injection molded strength, more or less, out of your 3D printed part. So you're getting engineering quality parts now out of this 3D printed filament using commodity polymers. It's not like this is super expensive material, right? ABS and polycarbonates. All right, so there we are. We started a business. It was originally called Reinforced Filament, and then we were acquired by this other company, Prepared for Flight. Then we're working on it. I developed a lot of this technology when I worked at the Army Research Lab. This was maybe 5-6 years ago, and it's really funny how this works, right? I wrote the patent while I was there. Okay, so the Army owns the patent. Okay, I'm an inventor on the patent, but they own it. Okay, so now I'm a faculty and I want to start this company, and now I have to license the patent from them. So I have to pay them to use my own technology that I invented, but I get a kickback on what I pay them because I'm the inventor. It's like, what the heck? Okay. But okay, that's how it works. But there you go. Okay, so I'm actually going to Boston area next week to make more of this filament and, you know, baby steps. There you go. Okay, that's it. I wanted to leave some time for questions, so I do want to have other people to talk about. The Army Research Lab, my advisor was Eric Wetzel. I had someone that worked with me quite a bit. His name was Ryan. They sent me a lot of funding. UMass Lowell, they have that machine that I put the ABS and polycarbonate, that double barrel. I had an undergrad working for me for quite a while, former military, actually ex-military, that was working with me. And obviously you guys for listening to me and getting your extra credit. Thank you.
So we have some time for questions. Let's fire away at Dr. Hart.
Go.
Was the pieces that you printed, were they all had 100% infill? And if they were, can you print parts that have like 10% infill and this still works?
Yeah, the pieces that we printed were all 100% infill that we tested. We have tested with other infill percentages, and it's not so much the infill, it's like number of layers next to each other. We find that if we have a single layer, it's a little unstable when you go through the annealing process, but if you have 2 layers that are sort of printed next to each other, like 2 rows next to each other, and you're sort of like stacking that on top of each other, it ends up working out still working out pretty well. Questions? Go.
How does not having 2 different, I know the extreme temperature can modify your print quality up a lot. Does the fact that the polycarbonate won't melt all the way change that?
Right. So if you're going to just only print ABS on a 3D printer, usually you print at like 230 C, right? If you're going to only print polycarbonate on a 3D printer, you would print usually around 300 C. So the question is like, what temperature would you print your dual material that has both ABS and polycarbonate? We settled on 280 C. That seemed to be enough to get the polycarbonate to flow correctly, but the ABS wasn't just like running out like water. You know what I mean? So it took a while to like figure that out. And I think if you had 2 polymers with more dissimilar glass transition temperatures, you'd start to run into issues of printing because, you know, the wider that you get with your TG margin, polymer number 1 is just going to start flowing like water, or polymer number 2 will just not print at all. So it's a shotgun approach. Try a bunch of different temperatures. Good luck and pray. Yeah, question.
With that temperature being so much higher than this cool ABS. Do you run into problems with like burning the ABS and like causing like fumes to happen?
Yeah, so ABS is made up of three components, right? There's acrylonitrile, butadiene, and styrene, right? So the acrylonitrile and the styrene, they actually make up like the matrix. So ABS is kind of like a composite in a way. And then the butadiene are these, they're like little particles. They're like the rubbery particles that actually kind of gives it the toughness. Usually when you smell ABS from printing, it's usually that butadiene phase. It's kind of like coming loose. And I don't know the exact numbers, but I would guess that you probably get more butadiene coming off when you're at a higher temperature. But I don't know the exact difference based on like the temperature of print. We hadn't seen any visible like charring, right? So there's a certain temperature that you get to where you start to get combustion, but that's more like 500 C, 600 C where you start to see that happen. So we're not really worried about like charring or combustion, but will there be more butadiene that's let off in the process? Maybe, possible. And that might change the toughness naturally. Yeah, interesting question. Do it.
What inspired the geometry of your skeleton?
It was kind of just a thought experiment, all right? Like, when you think about if you want geometry to be stable, at least this is kind of what we thought of, you know, brainstorming. Anyway. Let's go back here to this picture. Go. Yeah, that picture. This was our very first original idea, was having like this polycarbonate, and we thought that we needed it to go like all the way to the edges, so that when you 3D printed, you would have like a skeleton that was all like fully connected, right? So that you had just every piece touching another piece, so that there was no possibility of any like sagging or like loosey-goosey behavior, all right? So we wanted the polycarbonate to basically, we thought, go all the way to the edge of the circle so that they could touch each other. And then we thought, well, if it just goes to the edge, is that going to be enough? We were like, maybe we need like this little flange on the end so that they have a little bit more contact with each other, so that there's just a little bit better bonding, you know, between the layers. Turns out you don't need any of that, okay? You actually, after doing testing, only sort of need a small amount of like polycarbonate in here, and that's gonna just stop you from deforming during the process. So the original inspiration was just like, we know that we needed to go to the edges, or we thought that we did. How many spokes do we need? I don't know, 5 seems nice, okay? We can call it the strong star and be on our way, you know? There's probably a better solution than what we came up with. We just kind of like shotgun approach, like tried a bunch of different cross sections. So you see there, we had a bunch of different cross sections that we tried of the filament. The star, the small star is like, works the best, you know? There you go. There's probably more science to be done there, to be honest, but yeah, go ahead.
Yeah, how much does your high TG phase actually affect your properties? Like strength, anything like that?
So before or after, it's relatively minor influence. They're both miscible in each other, so ABS and polycarbonate are sort of like miscible into each other. I think if you had two really dissimilar materials, that might cause some problems because you do need some like adhesion between the two to keep things all tidy and neat. I think if you had one that might like shrink more than another, I'm thinking like a semi-crystalline material that might shrink a little bit more when it's coming through its transitions. That could be a problem. But since both materials here are amorphous, we didn't really see a lot of differences because of the two different geometries that were in there. I guess we never really measured like their adhesion to each other, so hard to like know for sure. But I don't, you know, just from a theory perspective, it seems like it shouldn't have much effect. But I guess I don't know 100%. Thanks. Go.
2 questions for you. What is the price per roll for a filament? And then have you guys done any impact testing?
Question number 1, what is the price per roll? We're not currently selling. We plan to sell our first round for $100 a half kilogram, which is expensive. I get that. But it's like the first run, you know, and as soon as our volume scales up to like traditional percentages, to me, it seems like there should be no reason why it comes down to the level of traditional 3D printing build, like a roll of ABS, a roll of polycarbonate. I think you could make this for that amount if you had the volume production to make that. Okay. The second question, have we done any impact? No, we haven't. That would be cool. I like the idea of impact, and I also like the idea of like sealing, like doing like a pressure test to like see when one would fail, and that's another like. I wish I had an undergrad to like do that project. I don't think it would like be that hard, and I could like do it pretty.
So if I asked them,
So you want to come to Milwaukee School of Engineering? No, I'm just kidding.
so I asked them if they got a little bit of experience with sealing. The company I work for, we build flow fixtures out of 3D printed materials for our research equipment.
Okay, cool.
And the only failure mechanism we had is when they're dropped from about 10 feet, they shatter.
Okay.
And so that's why I asked you that question. And then as far as the sealing go, we have not had any issues sealing the 3D printed material, but anything we mount to that is where we come across the sealing issues.
Yeah. Yeah, once those weld lines fail, you're going to have a path for escaping of whatever fluid you have, right? And I think that's the major issue. It's not that when you 3D print it, it's not that it's not sealed in the 3D printed case. It's that it itself is weak such that if it ever encounters any load, it will fail easily and break the seal, you know?
The testing I've personally done is I noticed about 3 meters cubed per second of flow loss due to a crack.
Okay.
To a single crack in the material.
I guess it would depend on crack size and things like that, but yeah. Okay, yeah. Interesting.
There's companies out there that make continuous carbon fiber filaments.
Uh-huh.
They anneal in the same way.
For 3D printing, are you talking like Markforged and stuff like that? So the Markforged and most continuous fiber 3D printing that I've seen, they actually don't use like a thermoplastic resin. They'll use like a UV curable resin most of the time. And so they'll lay down the carbon fiber in their UV curable resin, and they'll come on the backside with some UV or some other acrylate that is air cured is common as well. I think that's what Markforged uses. So for continuous carbon fiber, kind of a different technology.
I have seen some out there that do thermoplastic, but
Yeah, I've seen lots of chopped fiber thermoplastic, never continuous fiber. But it would be cool to see the continuous if there is continuous. I've never seen continuous.
so with the chopped fiber, do they do this?
With annealing, I've never seen chopped carbon fibers that have been annealed.
Would it hold its strength?
I
would
wonder.
assume it would.
I think maybe. I don't know. I would have to. It would be fun to try. Maybe I'll give it a try. Other questions?
How much does the annealing affect the?
Yeah, so we did a study where we made samples and put them on a DMA, which is a device that can measure deformations of material as you're going through a temperature change, more or less. Okay, and we see that the deformation change of our dual material filament during that annealing process versus deformation change that you might get of just, let's say, polycarbonate alone, which is a good control, is more or less, there's no difference between ours and theirs. It's like within 1% dimensional stability.
How long did it take you to come up with this idea, go through it, and get it up to your
I've been working on
production?
I've been working on this since 2016. So there you go. Yeah, it's been a while. I'm gonna break my hip next time I'm in the lab. I'm getting old. All right, go ahead.
Another interesting 3D printing technology is resin 3D printing. How does this compare structurally? My understanding of resin printing is correct. It's one piece rather than the layer line that you get with typical 3D printing. So
Yeah, most VAT style 3D prints, SLA is kind of like the preferred VAT style printing that you might have heard of. They still have like a layered structure. Even some of the best SLAs these days still have a sort of a layered structure. The way that more or less works is there's this vat, there's a UV laser that hits like the top of the vat, and that cures some of the material, and then the vat will like move down a little bit, and you hit it again with the UV laser. So there is like this discrete layering that still occurs, but this is a little outside my wheelhouse. But from what I understand, the welding between the layers in SLA is much better than the welding of FDM, which is the more traditional 3D printing. But FDM is much more common and widespread. A lot of people have FDM printers at home. There's not a ton of people that have SLA printers at home. So FDM, I think, is just a little bit more accessible for a lot of reasons, which is why we went that direction. Yeah. There's a lot of people working on resin formulations for SLA, though, I'll tell you. A lot.
Any other questions? Good one.
Back row.
Have you developed any technology that's using this material filament that isn't involved with the polycarbonate navy? Like, would there be any reason to do that?
So the material combination that we use is polycarbonate and ABS, mostly because that's the wheelhouse of their glass transition temperatures is the best for what we're trying to do. So their thermomechanical properties just end up being very good for us, okay? And the question is, well, what application might you want to use this material for that is useful, okay? So when you think about 3D printing, you would think about low volumes of production. You know, you're not going to make 1,000 items by 3D printing. It doesn't really make sense, okay? If you're going to 3D print something, it's probably something that's like highly customizable, that's like a one-off or a two-off or something like that. And so when you think about what our filament does, it provides a high strength, high stiffness, injection molded, very customizable piece by 3D printing. So what I think the best application might be is something like medical braces or orthotics, all right? Every person has a little bit of a different shape to their body. You need a foot orthotic to help you walk. You want to 3D print that because it's highly custom, it's a one-off, and the ones that you can buy off the shelf are just not going to fit your foot as well. But they still require a lot of strength. So we think that our filament is good for that wheelhouse. We've been talking a lot with the Army for frontline battle damage repair. So if something breaks in the field and you want a replacement part quickly, this can really work well for you because you can make something that's injection molded quality very quickly, one-off replacement part for, let's say, the trigger on your gun broke or something, okay? So that's kind of where we're seeing the technology or the application. But I think kind of the coolest thing is we sent this spools of these filament to like Army folks that like try to use them in the field. And some of the stuff that they come up with that's like really useful is like, one guy made a funnel and he was like, this is the best funnel like I've ever had for like draining oil from like his Humvee. He's like, I made this funnel, I like put it inside of an oven and I annealed it. And it's like, I couldn't get this in Afghanistan in like, you know, a 6 month, would take me 6 months to get another funnel, but instead I just like printed this one and now it's great. Right. And so like just those sorts of like one-off things where he's like, I just need a funnel. It's like, okay, well, that's very odd, but it's like works well for him. So, you know, you never really know until you like just put it in somebody's hands, it's going to like use it, right? Get it in the hands of smart people. Do that.
Okay, so I know some people have class, we'll let you get going here. Before we thank Dr. Hart one more time, I have 3 things. First of all, we want all the pieces back. So if you're holding a piece of filament or one of these show pieces, please bring it up. I need the sheets if you're in 216 where you signed in. If you didn't sign in, please do so. And then, to bribe you more, we're all headed to the mechanical engineering second floor called the Zoo. There's coffee and cookies and more chatting for more questions and stuff. So please join us over in the Zoo as you have time. And let's thank Dr. Hart one more time.